Hi, in this video I'm going to give you a quick walkthrough through this MATLAB example called lane and vehicle detection in Simulink using deep learning. Basically, this model uses an input video and it's going to detect lanes, the left and right lane, and also vehicles near the ego vehicle. So the output is going to look something like this. The yellow lines are the lanes, left lane, right lane, and the dots correspond to the dots in the polynomial line. And yeah, the vehicles are bounded by these boxes, which are described by upper left and lower right coordinates and their corresponding score. So both of these items are detected by neural networks, pre-trained neural networks, and then annotated back into the vehicle. Okay, so here's the model. Here's the first neural network to detect the lanes. And the lanes are modeled as polynomials of second degree. So, the polynomials are described as the coefficients of the second degree polynomial. So you have 3 elements for each lane. So you will have a total of 6 elements coming out of here, and the input is the image. But the image has to be resized into the size that the neural network tolerates. Okay, so after you get the coefficients, you're going to evaluate those polynomials into a range of horizontal values to get the corresponding y values of the real world coordinates. So then you have to apply an affine transformation to project them into the image, into the coordinates of the image. So you can get a list of lines. And then those lines are going to be annotated into the image in this component. For the case of detecting vehicles, it's a little bit more simple. The image is just given as it is to this vehicle detection using the YOLO network. The image apparently is going to be resized automatically, and the output is going to be the boxes delimiting the detected vehicle and their corresponding score, which both are also annotated by this one to supply the output video image. Okay, so to do the example, you have to hit open script, but there's a warning for Windows. Windows can generate a very big path, and then MATLAB can have trouble with it, finding the compiled binary file with source shalom file folder. So I would recommend to load the folder, copy the folder close to the root drive. Yeah, so here's the folder with all the files, and notice that I put close to the C drive, and that doesn't give me problems. If I just do it as is in Windows, it's not going to run. Okay, so the first step is loading the pre-trained networks, which are in these locations. I already downloaded them, so I'm not going to do it again. So I'm going to just load this map file to see the neural network using analyze network command. And in addition to that, you also have to get the video from this place. Yeah, I already had the video as well. And then you just open the model with this. Okay, in the meantime, I'm gonna take a look at the network. Okay, the lane net is the one to detect lanes. So that's a pretty small network. It's just a sequential network, convolutional. It's gonna use the max pooling to drop down the spatial dimension. It starts at 227 by 227. That's why we have to resize the image. And eventually we have a regression problem because the outputs are going to be the coefficients, the polynomial coefficients for the two lanes. So we have to bring down to 6 features. And these are real values. Okay, so we have 3 fully connected with drop-off regularization. Okay, so the YOLO network to detect the vehicle is a little more complicated. We cannot use the analyze command as is because this is a structure with multiple fields. Is the one that we are interested in. So let's take a look at the network. It's also a convolutional neural network. It's a little bit bigger. The input image size 224 by 224. That's why that's not the size that we supply to it in the Simulink model, which is 480 by 1600 something. So there must be some automatic resizing in there. Okay, so in here, in the first step, we bring down the the spatial dimensions using the convolution, perhaps by the stride, and then use max pooling for the rest. And notice that there's a common pattern, there's a residual connection in here, and that pattern is repeated multiple times. And also this is a regression problem because we have to detect the bounding boxes of the vehicle. Okay, yeah. Okay, so let's go now to the Simulink mode. So here's the Simulink model, so let's run it to just make sure that it works. It's gonna take a while. While it compiles, it's gonna compile only one time, and after that it's gonna run faster because it's already compiled. Okay, so here yeah, I guess my machine froze, but it's gonna I'm gonna pause that and run it again. Okay, I got it running. The reason why this takes to compile at the beginning of the first run, it takes more time to compile is because you have a MATLAB function block which are gonna be using code generation to wrap the generic code around S functions, and that is used within the simulation for. But once it is compiled, it's gonna run pretty fast. So as we see here, we already have the simulation up and running. So it's detecting the vehicles with the boxes with the corresponding scores, and the lanes are shown in yellow and the corresponding dots. Okay, so let's just pause this. And now we're gonna do some debugging. And one tip is that it is useful to see the base types and the dimensions of each line in the model. And to do that, you just go to debug and information overlays and select dimensions and base types. And once you select those, the model is going to update and show them. Okay, so these couple of blocks were not originally on the model, but I put them just to see the values within them. So they are just passed through. So we're going to see how the data looks in each one of them. Okay, and now let's gonna put this is basically resizing and rescaling. Okay, so we're gonna put a breakpoint here. We cannot put a breakpoint. Actually, we could put a breakpoint if we go Control U, go inside the neural network. Just gonna put a breakpoint there, although it's basically gonna use a precompiled library in order to run the neural network. So this is the place where the coordinates are converted from polynomial, are evaluated into actual lines that are going to be used for display. This is the YOLO network to detect the vehicle, and this is where the annotations are placed in the image. So now let's run it and see those breakpoints. Okay, so the first one that we're going to hit is this one over here. So let's take a look at how the maximum is 1 and the minimum is 0. So the values go between 0 and 1. And the size, as you might expect, is 480 by 640 and by 3. Okay, so now let's keep running. Let's take away this breakpoint. And now we're hitting this breakpoint. The breakpoint here was not hit. There's no breakpoint here. So in here, you're resizing the image from 480, 640 by 227 squared. And then you're going to multiply by 255. So the values are going to be rescaled to be between 0 and 255. Okay, so let's take a look at the maximum. This time the maximum is 255 because they were rescaled, and the size, as you might expect, it is this one that is the size that the neural network expects. So let's remove the breakpoint and hit F5 to continue. And now we're gonna hit the breakpoint in the neural network. And here we have no, actually it hit this breakpoint, not this one. So we already have the output. As you can see, the output of the neural network, the input is the image, 227 squared by the green blue, and the output is going to be the 6th element corresponding to the 3 coefficients of the left lane and the 3 coefficients of the polynomial of the right lane. So that's what we get in here. These are the 6 coefficients, and let's go inside of here to, whoops, doesn't want to go inside, so we're gonna have to open it manually. Let's hit Ctrl D. Okay, I'm gonna fix this problem. Okay, since the breakpoint was not hit, let's execute this command again to get inside of it. Okay, now we're inside the command, and the input is gonna be the 6 coefficients of the left and right lane polynomials. So we have the corresponding means and standard deviation for the two lanes, and usually when you have the standard mean, you subtract it, and the standard deviation you divide it. So by multiplying and adding it, going in the opposite direction, it's like denormalizing the data. Okay, so for some reason, the polynomial is a, b, and c, and if the absolute value of the c, which is the last element of the trio of the polynomial, the absolute value is higher than 0.5, then it's considered to be a good lane. So in this case, one of them is not does not meet that criteria, so we don't have lanes. So in the next time step, we're gonna get into here. Okay, so we're not gonna hit this point, but we're gonna see, we're gonna put a breakpoint here for the next run. Okay, so let's keep going, and let's keep going to the model, and now we are hitting this breakpoint here. Is the vehicle detection, the YOLO. Okay, so let's go inside of it, and again it doesn't want to do it, so let's just open it. Okay, again, it's not hitting the breakpoint, so let's just open the function, put a breakpoint here, and just reevaluate. Okay, now we're inside. Okay, so this persistent variable is like a state for the MATLAB function block, and it's gonna be initialized the first time it's executed. Okay, so since we don't have the detector yet, so it's loaded from the neural network that we saw from the math file, and then it's going to use the detect method from the neural network with the input image as an input, and it's going to give you the bounding boxes corresponding to detected objects. So let's take a look at how many objects it detects. So we have three boxes and 3 corresponding scores. Let's take a look in here with more detail. Okay, so notice for each row is correspond to one vehicle detected. So these are it should be either the upper left and lower right, or vice versa. And this is one box and the corresponding score, another box corresponding score. Okay, so let's keep going. Let's take away this breakpoint from YOLO detection, because now we're gonna go to the annotation part. Okay, we have to hit F5 again to keep going, and now we are in annotation. This one is the one that takes the vehicle detection data and the lane detection data, and it's gonna put it into the image. Okay, so since we are having problems with the breakpoint, we just get the corresponding function directly, the annotation, and we're gonna put a breakpoint here. Okay, let's go back to here and then just execute it. Okay, so we can see the inputs. We don't have a lane yet. In this time step, we don't have lanes, but we do have 3 vehicles detected, and we're gonna see how they are annotated into the input image. So let's run it. And now we hit the breakpoint, and we have bounding boxes. So this is gonna use this computer vision method to annotate the rectangle. So we give the coordinates, and it's gonna create the rectangles in the image. And let's take a look at the image to see how it looks before and after. Okay, so if the image is blank, and most likely this is gonna be the vehicle detected. We have possibly 3 vehicles. So let's take a look at how it looks after using the 3 bounding boxes. Okay, let's take a look again. Okay, so here are the 3 vehicles. This is the corresponding scores for them. Okay, so for lanes, we don't have a lane found, so this is just gonna skip. Okay, so we're gonna run this until we get a lane detected. Okay, let's just keep running. Okay, now we're back in lane detection coordinates. Okay, so now let's see if we are able to hit this. Okay, we finally got the left and right lane in the image, so we are able to hit this breakpoint. So we are in here in this place. Okay, so the first thing to do to compute basically convert from the polynomial coefficients, evaluate them into actual coordinate values. We're gonna we have this set of x coordinate values that go from 30 to 30. It's a total of 28 values, and then we're gonna evaluate into the polynomial. So we get the coefficients for the right lane and the coefficients for the left lane. So let's go inside of it and see what happens. So yeah, it didn't get it. So again, we have to open this and reevaluate. Okay, since the breakpoint is not hitting, let's evaluate this with F9 just by shadowing the command. Okay, and that gives us the result. Just let's put a breakpoint into the corresponding function and try it again. Now, okay, so basically to compute the values, you have the set of x coordinate real world values that are evaluated into a polynomial. And let's take a look at the help for this. Yeah, so basically what this does is that it takes as an input the vector that represents the coefficients of the polynomial. In this case, we have three coefficients, a, b, and c, because we have a degree of 2. And then it's gonna take the x values that are going to be evaluated in the corresponding polynomial. So it could be just one value, and for that value you're gonna get a corresponding y. So the x, let's say that is 0, then in here you're gonna get 1 in the output. So if you provide a vector in here, you're gonna get a vector of the same size in here. So in here we have 28 values, so you expect 28 values out of here. Exactly 28 values. Okay, so let's just hit F5. So let's go back in here. So now we got real world coordinates for the polynomial representing the left lane. The right lane. We're gonna do the same for the left lane. So we have to project those real world coordinates into the coordinates of the image, and in order to do that, we get this transform. Okay, so let's run it. So we could not get inside of it. So let's take a look. Just put a breakpoint in here, and then run it again with F9. Okay, so it's gonna use the yaw, pitch, and roll parameters from the camera. It's gonna get a translation matrix, which is defined in this example. So let's just run it. Okay, so it's gonna use the sensor location, the height, and it's gonna get the rotation matrix using the yaw, pitch, and roll. And here you have this is not like the usual positions that you see, the cosine and sine for rotation matrices, but it looks like it has a particular axis of rotation. Okay, so then the sensor locations are gonna be used to get the translation vector. So the translation vector comes from this position, is 0, 0 and the height, and then you just multiply by rotation matrix, and we have the translation vector. Okay, that is going to be put together along with the rotation matrix. Let's go to the rotation function. Let's put a breakpoint here. Let's go inside of it, and it's going to use again the yaw, pitch, and roll. So we're gonna get a 3x3 rotation matrix, and notice that the cosine and sines are in different locations. So this is a different axis of rotation. It might be good to have like a visual reference of this, but the example doesn't provide one. So what it's gonna do is gonna use the focal length and principal point, additional parameters of the camera, and with that it's gonna create this matrix. So let's take a look at this function as well. should be somewhere around here. Okay, let's put a breakpoint. Okay, now let's evaluate it here like this. Okay, so yeah, using the focal point and the principal point, we're gonna get a 3 by 3 matrix, and so that's gonna be multiplied against this affine transformation that uses the rotation. Yeah, so you can see the translation below and the rotation above. And this is a 4 by 3, 4 rows, 3 columns. The columns must match the row of this matrix, which is 3 by 3. So the corresponding output matrix is going to be 4 by 3. And now we drop the C coordinate. And now basically we get a projective matrix, but this is just wrapping the transform matrix into a structure, and you're gonna see why. Because this is just a couple of fields where T is the same matrix that we have above, and you can see that it is the same. And yeah, so now we're gonna invert the matrix, so that matrix must be singular, and now with that inversion we're gonna use it to get the coordinates for the points of the lanes. So now we have the transform, and we use this method to convert the x coordinates and the y coordinates into coordinates that correspond to the image. Okay, so this is 28 by 20 x points and 28 y points. So we're gonna have 28 pairs of x and y's, and these are our coordinates. And we do the same for x, for left lane, right lane, and we say that we find a lane. Okay, so now that we have the lanes, we're gonna put a breakpoint into the annotation to see how they are placed into the image. Okay, so let's just keep running. We hit this breakpoint, and since it's not obeying the breakpoint, just let's do it manually by placing a breakpoint here and executing this. Okay, let's just F11. Okay, so yeah, now we're in. Okay, so we have 3 vehicles detected, so they're gonna be again inserted into the image. So you're gonna see 3 boxes into the image. Yeah, for some, this might be an error from the YOLO train network. So we're able to detect the other 2 vehicles. Okay, now we're gonna insert the points, and so we're gonna create for efficiency the structure of the output points, which is going to be 20 by 4, because we have a total of 28 points. So we, instead of seeing the 2, we see 4, because we have x and y of the start of the line and x and y of the end of the line. So you're going to see a chain of lines where the last point of the previous line is going to be the first point of the next line. So that's what we're going to do in here. We're going to have an initial previous point, so iterate from the second one, and with this we get the 4 points, 1 to 4, and then the next previous point is the current point. Okay, so let's just put a breakpoint here. Okay, now we have the points, and we're gonna use the insert shape, which is a computer vision function to insert all these lines into the image. Okay, so let's take a look at the points. So let's take a look at the first point, all the points. So we have 4 elements, x and y for the first coordinates, x and y for the fourth one. It looks like this one doesn't have much, but let's take a look at the number 7. So yeah, the starting point, xy, end point, xy. So let's take a look at the next one. Notice that this point is the same as this one, so the end of the first line is the start of the second line, so they are connecting lines to form the polynomial. So it's going to insert the all the lines. So now let's take a look at it into the image. Okay, for some reason it's showing everything all at once, but at the end, basically this insert shape is gonna put the yellow line, and after I execute this one, it's gonna put the other line, the yellow, and the insert marker is gonna put all the points, which are the original left points and right points. I'm gonna put them as green dots in here. So that's what you're gonna see in the image. Okay, so let's just keep it running. Now there should not be any more breakpoints. Let's get rid of the breakpoints so that we can see the video. Okay, after removing the breakpoints and recompiling the model, then it's running back to normal. Okay, so that's all I have for today. Thank you very much for your attention.